Hello everyone, welcome back to my channel. Hope you all doing good. I am Tejaswini, pursuing my third SEM BE in Computer Science at Sri Venkateswara College of Engineering, Bangalore. Today's title is Mathematics and the topic is Test of Significance for Large Samples. First we'll move on to introduction. Test of significance is a fundamental concept in inferential statistics that helps researchers determine whether the observed data in a sample is strong enough to make inference about a population. When we deal with large samples, these tests become even more powerful, allowing us to draw more reliable conclusions about population parameters. And let us know what is test of significance. A test of significance assesses whether the observed data in a sample differs significantly from what we would expect under the null hypothesis. It helps researchers make inference about a population based on the information gathered from a sample. The process involves formulating null and alternative hypotheses, for calculating a test statistic and comparing it to a sampling distribution. This comparison leads to a decision about whether to reject or fail to reject the null hypothesis, ultimately guiding our understanding of the data and its implications. Next, we have a null and alternative hypothesis. Null hypothesis. The null hypothesis, represents the status quo. The default assumption we're trying to disprove. It's a statement about the population parameters we are interested in. For example, a null hypothesis might state that there is no difference in the average height between men and women. And the next is the alternative hypothesis. The alternative hypothesis, H1, contradicts the null hypothesis. It represents the claim where we are trying to supports with evidence. In our height example, the alternative hypothesis would be that there is a difference in average height between men and women. Next is the test statistic and sampling distribution. First, we know about the test statistic. A test statistic is a numerical value calculated from our sample data. It summarizes the evidence against the null hypothesis. In the case of a z-test, the test statistic measures how many standard errors the sample mean is away from the hypothesized population mean. Next is the sampling distribution. The sampling distribution represents the distribution of all possible sample means if we repeatedly retrieve samples of the same size from the population. It helps us understand the likelihood of obtaining a sample mean as extreme as are if the null hypothesis is true. Next we have a z-test for large sample size. The z-test is a powerful tool for hypothesis testing when dealing with large samples. It relies on the central limit theorem, which states that the distribution of a sample means approaches a normal distribution as the sample size increases. This normality allows us to use standard normal distribution table to calculate probabilities and make decisions. Applications. Z-tests are widely used in various fields including healthcare, finance and marketing. They can be applied to test hypotheses about population means, proportions and variances, providing insight into the underlying characteristics of large populations. The next and the formula for z-test is z is equals to x bar minus mu naught divided by sigma divided by root n, where x bar represents mean of a sample, mu naught represents mean of population, and sigma is the standard deviation of population, and n is number of observations. Next is assumption and conditions for z-test. First is a random sampling. The data should be collected using a random sampling method to ensure that the sample is representative of the population. This helps to avoid bias in the results and ensure that the conclusion drawn are applicable to the broader population. And the second is a large sample size. The sample size should be large enough to ensure that the distribution of a sample means is approximately normal. A general rule of thumb is that the sample size should be at least 30. Next is the population standard deviation known. The z-test requires knowledge of the population standard deviation. If it's unknown, a t-test is typically used instead. In some cases, a good estimate of the population standard deviation can be used, but they should be carefully considered. Data distribution. The data should be approximately normally distributed, while the central limit theorem ensures normality of sample means for large samples. The original data itself should not have extreme skewness or outlier that could significantly distort the results. And the next we have one-tailed and two-tailed z-test. First we'll know about the one-tailed test. A one-tailed z-test is used when we are interested in testing whether the population parameter is greater than or less than a specific value. It focuses on one tail of the distribution, either the upper or lower tail depending on the research question. Next we have a two-tailed test. A two-tailed z-test is used when we are interested in testing whether the population parameter is different from a specific value. It considers both tails of a distribution, focusing on whether the sample means fall outside a specific range around the hypothesized value. Next is a p-value and decision making. P-value. The p-value represents the probability of obtaining a sample mean as extreme as r if the null hypothesis is true. A small p-value, typically less than 0.05, indicates that the observed data is unlikely to have occurred by chance if the null hypothesis is true. Next is a decision rule. If the p-value is less than or equal to the significance level, means alpha, we reject the null hypothesis. This means there is sufficient evidence to suggest that the alternative hypothesis is true. If the p-value is greater than the alpha, we fail to reject the null hypothesis, meaning we lack sufficient evidence to support the alternative hypothesis. Next we have type 1 and type 2 errors. First is a type 1 error. A type 1 error occurs when we reject the null hypothesis when it's actually true. This is also known as a false positive. It's like wrongly convicting an innocent person in a court of law. The probability of committing a type 1 error is denoted by alpha. Next is a type 2 error. A type 2 error occurs when we fail to reject the null hypothesis when it's actually false. This is also known as a false negative. It's like failing to detect a disease when a patient is actually sick. The probability of committing a type 2 error is denoted by beta. And next we have practical considerations and limitations. First is the sample size. A larger sample size generally provides more power to detect true differences. However, there is a trade-off between a sample size and resource available. And second is assumption. The z-test relies on certain assumptions. If these assumptions are violated, the results may be unreliable. Third, we have statistical significance versus practical significance. While a statistically significant result may indicate a difference, it doesn't always translate to a meaningful or practically significant difference in the real world. And the last is a context and interpretation. It is important to consider the context and interpret the results within the context. Don't overgeneralize or draw conclusions that aren't supported by the data. The conclusion: in large-scale studies, statistical significance often highlights even minor differences as meaningful due to the increased power of large samples. However, interpreting such results requires careful consideration of their practical significance, as small but statistically significant effect may not have real-world impact. Conclusions should therefore integrate statistical findings with the context, effect size, and study design to ensure that the results are both robust and meaningful for practical application. That's all for this video. I hope this may be useful for you. Thank you. Have a nice day.